Okay, great. Let's get going. So my name is Brian Vanderwend. If you haven't been in a tutorial that I've led before, I'm a member of the CISL Consulting Services. So we're the folks who, answer the help tickets and also install a lot of the user-facing software on Cheyenne and on Casper. And as probably everybody who's here knows, we're in the middle of this transition of the Casper system from the Slurm job scheduler to the PBS Pro job scheduler. So the topic of this talk will be how to use PBS in the Casper context. If you're familiar with PBS already on Cheyenne, this will hopefully eliminate some differences and also just give some insight into how it's been set up on the Casper system. So feel free to put any questions you have into the chat, and my assistants here will help just interrupt me with those questions whenever they're pertinent to the slide. So feel free to put in questions at any time. You don't have to wait till the end. With that, we'll get started. So the first thing to note really is that our Casper resources themselves have been significantly expanded. This has been tangential, I suppose, to the switch to the PBS scheduler, but these new resources have only been available via the PBS scheduling on Casper. So we have 62 new high throughput computing nodes, these what we're calling HTC nodes, and we also have 2 new high memory nodes. And I'm just going to do, it's going to be a bit of an eye chart of a slide here, but I'm going to do a summary of all the resources that we have on Casper now, because it's becoming more heterogeneous over time, and I want people to be aware of the different resources they have access to. So we have these high throughput computing nodes. These are for data processing and analysis workflows that either require less compute or more memory, node memory, than a typical Cheyenne job. And in that population, we have kind of the original set of Casper nodes, and then we also have these new ones that we've brought online. So there are 13 nodes with Intel Skylake CPUs. That's a prior generation. And then we have these 62 new nodes with Intel Cascade Lake CPUs. And that's important to note just because if you're going to compile, let's say a C or a Fortran code that you want to run on Casper, you'll want to compile it on the older architecture, or you'll want to be very careful about what optimizations you use, because if you use optimizations that are only supported on Cascade Lake, you might run into some problems at runtime if you run that on Skylake. So generally, you can request a Skylake node if you're doing compilation. Important to note, the 2 Casper login nodes we have are Cascade Lake, so those are actually kind of a tricky place to do compilation. So those, either way, whether regardless of the CPU architecture, there's 32 CPU cores per node. In Slurm, we actually scheduled based on hyperthread, so there were 72 slots on a node, but in PBS, we've decided to go with just the physical cores. So there's 36 cores to schedule, and that kind of keeps things simpler in terms of that you have access to an entire physical core and you're not sharing those resources with anybody else. And then there's 380 gigabytes of memory per node. So if you're familiar with the Cheyenne nodes, then you'll know that there's either 45 or 109 gigabytes of usable, depending on the type of Cheyenne node. So this is significantly more. The other thing that perhaps most people know on Casper, but if you don't, all the nodes have local solid state drives, this NVMe storage, and we have that set up to be, it's usable as an explicit swap space, but it's also implicitly used to augment memory. So if you end up using more memory than you have access to, your work can run in a swap space as well, and I'll explain kind of the implications of that later on. So then we have these high memory nodes. There's only 2 of those at the moment, so this is really just for CPU-only tasks that require exceptional amounts of shared memory. So that's the node memory on a single node. You're not going across nodes with MPI. We have the 2 with Cascade Lake CPUs, pretty much similar stats, except that they have 1.5 terabytes of memory per node rather than the 380 gigabytes. So this is really if you have extremely large data structures that you need to fit into a single node. We have our graphics and visualization nodes. So these are for things like 3D rendering using, say, Vapor, PyroView, or Visit, and also for running remote desktops. You would typically run those on these nodes. And the reason that these are appropriate for that is because they have the NVIDIA Quadro GP100 GPUs. So these are I guess, if you want to call them weaker, but they're the GPUs that are more targeted towards visualization, not towards general purpose GPU computing. You can see that those otherwise have similar statistics to the older Skylake HTC nodes. There are 9 of those. And then finally, we have our general purpose GPU nodes. So these are really the workhorse GPU nodes. They're for developing, testing, and running GPU-enabled models, and also for running GPU-powered machine learning libraries, like, say, all the Python machine learning libraries that are out there, for example, that have GPU capabilities. And we have 4 of those nodes that have 4 NVIDIA V100 GPUs. 2 of those have Skylake CPUs, and 2 of them have Cascade Lake, and all of them have 768 gigabytes of node memory. And then there are these 6 nodes that actually have 8 V100 GPUs, and all of those have Skylake CPUs and over 1 terabyte of node memory. And otherwise, they have 2 terabytes of the NVMe, solid state disk, and then 32 gigabytes of GPU RAM per GPU, so per V100. So sometimes, you may be limited by memory, but it's actually the GPU memory that you're limited by and not the node memory. So that's something to be aware of as a distinction. And then just to give you a heads up, we have 4 dedicated nodes for the research data archive as well. And those exist to really keep the RDA workflow jobs off of the general use nodes, but those jobs will show up in the scheduler output. So if you see a lot of those RDA jobs, that's why they're there, because they're using the same PBS. So from the scheduler side, what we're doing is we're working towards a single scheduler environment. So for a while, we've been running PBS on Cheyenne, and we've been running Slurm on Casper, and that's worked okay, but there's definitely been desire to have a single scheduler running across the complex, and that's something that we want as well, because it just simplifies a lot of things and people don't have to maintain 2 sets of job scripts. So our situation as of today is that we have the PBS server on Cheyenne, we have the PBS server on Casper, and then we still have the Slurm server on Casper, and about half of the existing Casper resources, the old Casper resources, are split between those 2 schedulers. And if you want to go from Cheyenne if you want to submit a job from Cheyenne to Casper, then you need to run this qsub Casper command, which I'll explain in a little bit. And then if you want to go to Slurm, you would do sbatch or srun, depending on whether you're doing interactive or batch. Now, in about a week's time, on April 7th, that Slurm server will be retired, and then we'll just be running PBS on both systems. We'll have the PBS server on Cheyenne, and we'll have the PBS server on Casper. And it's important to note that I use that terminology specifically because in PBS's documentation, it refers to a different cluster as being a distinct PBS server if you're running multiple servers. And since we're running multiple servers, what this means is that Cheyenne queues will not show up in, or will not be available to PBS commands on Casper, and vice versa, which is why we have this qsub Casper command to send jobs back and forth. But what we're aiming for, and the current expectation is that this will be sometime in the summer, is to run everything on a single multi-scheduler basically PBS instance. It's actually still multiple servers, but it's all in the same PBS instance. And then you can just use qsub to submit, and the ultimate goal is to have all the queues visible to all the commands at once, and have neat things like job dependencies between Cheyenne and Casper jobs. And then moving forward even further, when the follow-on to Cheyenne, NWSC3, comes online next year, we aim to have that same capability working there, so that you'll be able to have workflows that go between the main compute system and the data the data analysis system. Okay, so let's give an overview of how PBS Pro scheduling works on Casper. And again, this will look pretty similar to how it works on Cheyenne. You'll submit a batch or an interactive job with QSub. So the batch job would go with QSub. An interactive job, we have a convenient script called exec Casper, and we'll detail all of these in coming slides. And then if you want to go from a Cheyenne login node, if you want to submit a Casper job from a Cheyenne login node, you would have to use this QSub Casper command that we've provided. So the jobs are initially submitted to a queue that is just called the Casper Queue. And in PBS terminology, this is what's called a routing queue. And again, I'll explain what that means in a bit. But the Casper queue is similar to the DAV partition in Slurm. So it's a single destination for all of the jobs, and you don't have to, think too hard, I suppose, about where your job exactly is going to land. It's more based on the resources that you're requesting, which is how we have it set up in Slurm. So then PBS will conditionally route the job to an execution queue, and that's based on the specific resources that you request. So while you'll submit to this Casper queue, where your job will actually run is in one of these execution queues that's based on your resource selections. And then your job will start with a default environment on Casper. This is the same thing this works the same way it did in Slurm, that your environment basically gets cleaned from your login environment to your batch environment. And that is really because we're running two different operating system environments between Cheyenne and Casper. So on Cheyenne, we're using SLES Linux, and on Casper, we're using CentOS. So propagating the environment forward from Cheyenne would cause problems in the job. So we just provide you with a clean environment, which is actually what the PBS Pro documentation specifies anyway. There are ways to override that for certain settings if you'd like. But generally what you want to do as a result is you want to load modules and set environment variables at the start of your job. So you basically, have the mindset that you're starting off with a clean environment, and that you should set it up as you wish to have it set up for your job. Now your startup files will be loaded. If you're a bash user, your .bashrc or your .profile, and if you're a C shell user, your .tcshrc or your CSHRC, depending on which one you use. So those settings will be imported into your job. And just to give a little graphical there, so what you'll do is you'll submit to this Casper queue, and the job will execute on one of these execution queues. And that these follow those general node classes that I described before. So we have our HTC execution queue, our large mem, our viz, and our GPGPU. So if you run a QStat and you see, a job that you've submitted, odds are it's going to be listed under one of these execution queues. It's not going to show Casper under the queue category. So don't be confused by that. It's just that PBS has already routed your job to the execution queue that it will eventually run on. Okay, so submitting batch jobs with QSub and QSub Casper. The format of the batch script should look very familiar to any Cheyenne user. There are some subtle differences that you'll notice here, but basically, we have our batch directives here. These resource statements are I think the thing to really note. You want to do basic environment setup again, like set up your temp dir, just so that your temporary files are written there instead of into the temp space, which is less, something you can't rely on as much, I would say, since it's a shared resource. You'll want to set up your environment. So in this case, I'm just running a hypothetical machine learning script, but I'm loading Python on top of the default modules and then activating the system environment. And then I like to do this in a lot of my PBS scripts. I'll just do a QStat with a long form output. And this gives me a lot of detail about my job after the job is run. And it'll give me some information about like resource usage and wall time usage and things like that. So that can be useful for debugging as well as estimating the resource needs you have moving forward. So when I have my script here, basically what I'll do is if I'm going to submit from Cheyenne to Casper, I'll do QSub Casper ml script.pbs. This is just the name the convention I like to use. If I submit from Casper, then I just use the QSub command. And this is something that, you just kind of have to be aware of where you are in the system for now, because if you run QSub and then the script from Cheyenne, you'll get an error. And if you run QSub Casper on Casper, then that command isn't found either. So this is just a distinction that we have to maintain until we have that unified PBS setup that I talked about in the prior slide. And then as batch script here, we're requesting a 10-hour job. So you can see I'm setting the wall time here to 10 hours. I'm asking for 8 CPU cores in this select statement, and CPUs equals 8. 40 gigabytes of node memory, so that's an important distinction there. This mem only specifies the node memory, doesn't have anything to do with the GPU memory. But I am also asking for 1 GPU in this select. And then there's a separate resource specification here of GPU type, where I'm making sure that it's a V100 GPU because I want to run this machine learning code. Whereas if I was doing a visualization task, I might ask for a GP100 instead. So the resource request fundamentals in PBS Pro are a bit different than they were in Slurm. In Slurm, we had the G-res, which is how you would ask for like a V100 GPU and how you would reserve one. And then you had feature constraints as well. You could specify like a Skylake constraint or a GP100 constraint or an X11 constraint. So in PBS, we have these resource specifications, and there are 2 types. There are job resources and chunk resources. So a job resource, well, I guess first off, a job will consist of 1 or more chunks, and these chunks are just, what you can imagine. It's a chunk of resources. But job resources will apply to all of the chunks that you request, whereas obviously a chunk resource will only apply to a specific chunk. And here I summarize kind of the relevant resources in each of these categories. So things that will apply to your entire job are things like wall time, the GPU type, if you specify that, CPU type, if you specify that. And then there's also this place one, which I won't really go into detail here, but it allows you to control the placement of those chunks that you request. So maybe you want the chunks scattered across multiple nodes, or maybe you want the chunks packed into a single node. You can use that statement to specify that. And if you do if you look at the manual page for QSub, or if you look at the PBS user guide, it'll give you a lot of detail on using the place statement. Now, these chunk level resources are things like the number of CPUs, NCPUs, MPI tasks, OMP threads, NGPUs, so the number of GPUs, and then the node memory mem. And these apply only to a particular chunk or a collection of chunks. And then so another thing to note is that each job resource is specified in its own directive. So each of these hash PBS lines is a directive. And then the chunk resources are all collectively specified in a select statement here. So
Brian, we have a question.
Sure.
Anne asked, does the QSub versus QSub Casper apply to the login nodes?
So it applies to running a QSub on a login node. It's not pertinent to accessing the login nodes. So, you would still SSH to Cheyenne to get to Cheyenne and SSH to Casper to get to Casper's logins. But once you want to submit a batch or an interactive job, then yes, it applies to basically the login environment that you're submitting from. So if I'm submitting a Casper job from the Casper logins, I want to run QSub. And if I'm submitting a Casper job from the Cheyenne logins, I want to use QSub Casper. Please let Mick know if that didn't clear it up. So just to finish this off, so in the job level specification, we have this example of I'm setting the CPU type to be Skylake, and this goes on its own line. So I'm just setting a single specification here using this -L. That's PBS's notation for a resource statement. And then for the chunk level resources, they all go into a single line of the select. And the format here is I'm asking for 2 chunks, and then I'm specifying all the details of the chunk afterwards. So each of these 2 chunks has 8 CPUs, and 80 gigabytes of memory. So in total, my job will have 16 CPUs across two chunks, which may be nodes, and 80 gigabytes of memory, or sorry, 160 gigabytes of memory total, 80 in each chunk. Now, the way we have it set up by default, typically these chunks would be spread across multiple nodes, but that's not a guarantee. It depends on how this place this place flag is configured. So you can kind of think of a chunk as a node, but it's not going to be the case in every circumstance. Okay, so that's a bit about batch jobs. So submitting interactive jobs, you can do that with QSub. There's a QSub-I form, but we provide this exact Casper script, which will hopefully simplify things a little bit, shorten the syntax a bit. So it provides a simple command for starting an interactive session. It's basically the PBS version of our execdav script to get an interactive session in Slurm. And it'll give you a similar default resources. If you don't give any arguments, it'll give you 1 core on 1 HTC node. It'll give you 10 gigabytes of node memory, and it will give you a 6-hour wall time. Unlike Slurm, all the resources on the primary node are always assigned to the shell and are thus available to any programs you run. So in Slurm, it was kind of tricky because Slurm allocates resources to your job, and then you can run a shell within that pool of allocated resources, but the shell that you run, like Bash or C shell, might not actually be assigned all of the resources that you've allocated to your pool. And that has some benefits in that you can really say, okay, I'm going to use like 5% of my resources for the shell, and then I'm going to make sure that 95% are available to like my program. But PBS doesn't make that distinction, which does simplify things in other ways. So I tend to like the PBS way of doing this. So any program that you run in your shell, which will be a sub-process of that shell, will have access to all of the resources in there. Obviously, that's only on the first node that your job is running on. So if your job spans multiple nodes, you'll need to use MPI to get access to all of the resources across the nodes if you want to have your program access that in its environment. But on a single node, you'll have access to all the resources in a shell. Now you still have to, of course, specify a project that this job will get submitted against. So you can use the -A flag, which is the native QSub flag, or you can also set this dav project environment variable. So in C shell it'd be a set env, and in Bash it would be an export. And if you set that in your startup files, then you'll have that available all the time. So you won't have to put in a project every time. If you don't specify any project, then exec Casper will give you it'll kind of just pick a project from your list of available projects, which might work out, but certainly recommend that you specify this explicitly. And then all QSub flags are supported by exec Casper. So like the -L wall time, -L select, anything that you want to customize, you can do. Now, there's certain things that might not make sense, like there's certain flags that are particularly pertinent to batch jobs. So if you specify those for an interactive job, like if you tell your job to block, which basically means PBS will block your shell until the job finishes, then that's not going to work well in interactive mode. But any of the common flags that you might want to specify are supported by exec Casper. And then just to show you a little example here, so in the first case, I'm setting the project in the shell, C shell in this case. So I have the set env dav project, and then I specify my project code. And then I start a 2-hour session on an HTC core using exec Casper. So the only custom setting I'm doing is this -L wall time equals 2 hours. And one important thing to note is that for exec Casper, we've made it so that it works the same either way, whether you're on Cheyenne or on Casper. So you don't have any distinction there like you do with the QSub command. We handle all of that internally for you in this exec Casper command. So you don't have to change your syntax based on where you are. Now these, yeah.
Brian, there is one question. Okay, Julie, you just answered Julie's question. Thanks.
Oh, sure. Good timing. So for the second example here, you can see how this gets a little bit verbose sometimes. If, let's say I wanted to ask for 18 MPI processes in my job, 4 V100 GPUs and 100 gigabytes of known memory. So I would have this big select statement of, the NCPUs equals 18, MPI tasks equals 18, NGPUs equals 4, and memory equals 100 gigabytes. And then I'd specify the GPU type as V100. So this is a bit cumbersome to type out. So what we've also added are these quick specification flags in exec Casper that you can use to easily customize resources. And I want to emphasize that these are flags that we've added to exec Casper, so these won't work if you run QSub. So that's just an important thing to keep in mind. But these custom flags will allow you to quickly modify a single resource without respecifying the entire select statement. The downside, I suppose, there is that if you want to have multiple chunks with different types of resources, like a heterogeneous collection of resources, then this doesn't give you that flexibility. So here, if I ask for, say, 10 MPI tasks, that's going to be 10 across all of the chunks that I request. But within that limitation, these I think cover most of the types of requests you would want to do. So it allows you to specify the number of chunks, the number of MPI tasks, the number of OMP threads, and GPUs and mem. And it uses the same, as you can see, it uses the same nomenclature as the select statement. So, just to drive this home, these two calls to exec Casper both request the same thing. They both request a single core, a single CPU core with 20 gigabytes of known memory. And if I use the native QSub formulation, it would be this -L select equals 1 and CPU is 1, mem equals 20 gigabytes. But since the default in exec Casper is to give me one CPU core, I could just use this mem equals 20 gigabytes here, and that will customize this select statement to add that memory specification onto it. And we've designed exec Casper that before it runs, it will show you the exact QSub line that it's going to submit to the scheduler. So you can use that to kind of sanity check what you've inputted. Okay. So just a little bit about job dependencies in PBS Pro, and this should look pretty similar to, again, if you've used these on Cheyenne. Dependencies are also similar to the Slurm dependencies. The main ones that you would focus on would be these four. So after all the jobs in the list that you specify have started, whereas after OK and after not OK would be after all of the jobs in the list have finished and either succeeded or failed, depending on which of those two you use. And then after any would be all the jobs in the list that have exited with any status. And in my experience, the after OK condition is the one that most people use. An important point here is that dependencies, as I mentioned early on, are not yet supported between Cheyenne and Casper Jobs, but that is the ultimate goal. So at that point, we'll have some added capability, but also a little bit added complexity there, and we'll describe that when that capability comes online. But just to show you a quick example, let's say here's a job that I have where I'm running a GPU, an MPI-enabled GPU model. I want to run the model in a script. This is an important thing to keep in mind. I want to run the model last in my script to make sure that the exit code that is used by PBS to denote whether the job has succeeded or failed actually comes from my model execution. Or whatever the command that you care about at the end to signify a success condition, you want that to be at the end. So you want PBS to get that exit code. And there's a particular caveat with CShell here. So CShell actually has a file called a .logout file that you can put in your home environment. And if you have something in that .logout, it will override the status of your last command. And typically the .logout will succeed, so it'll make PBS think your job has succeeded, even though maybe the model has failed. So in general, I would just recommend not having a .logout file in your collection of shell .files in your home directory. If you don't even know what that is, then no problem. But if you're using that, then it's just something to be aware of. And then just to wrap this part up, for submitting the jobs in the command line, you would, and this would be for a bash user. This is the bash syntax. So here I'm storing the job ID from my Q sub of the job of the first ensemble member, the job ID of the second ensemble member, and I'm storing these in environment variables. And then I'm specifying them to Q sub for my post-processing job using this -w depend equals after OK colon job ID colon job ID. And you can extend that list as long as you like. So this part of it is pretty much exactly the same as Slurm, the after OK colon. It's just that instead of -- dependency, it's -w depend equals.
Brian, we have one question from Seth.
Sure.
Any general ballpark on when cross-system dependency is likely to be implemented?
Yeah, so a general ballpark would be, I'm really hoping this is online by the summer. More specific than that is tricky because there's a separate issue in PBS that we're waiting on the vendor Altair to resolve. And once they get that resolved to our satisfaction, then we can upgrade the version of PBS on Cheyenne. And once those two versions are in sync, then we can hopefully enable that cross-server dependency capability, along with a lot of other capabilities that having cross-server interaction allows. So yeah, unfortunately, I can't give like a more narrow time frame than that, but the hope is that sometime this summer we'll have that available. And if it comes sooner because Altair really is on the ball, then that's great. But I think that's what you should expect.
Yeah. Seth, I'd also point out that to do so would require a full system outage. And, we're trying to, on Cheyenne, and we're trying to keep those to a minimum. So that's also one of the things we have to work the logistics with.
So one thing to note, this is similar to Slurm, but it's different than Cheyenne. So unlike shared jobs and the share queue on Cheyenne, the resources that you request are exclusive. So that means that any CPUs and any node memory that you request are reserved for exclusive use by your job. And no other jobs, including your own, can access those resources. If I ask for 20 gigabytes of memory, then I have exclusive use of that 20 gigabytes. I'm guaranteed to have 20 gigabytes. So it really does reduce, I guess, variability in the resources that your job has access to. So this is overall a good thing. Similarly, the V100 GPUs are also scheduled for exclusive use. So if I ask for 4 of those, then I have exclusive use of 4 of those GPUs. Just one thing to note, that NVIDIA has this multi-instance GPU capability. That's not currently supported by PBS this time, although they are working on it. So the MIG mode basically allows it allows a V100 to be partitioned into multiple GPU instances and have multiple users be in cordoned off areas of the GPU and have guarantees of X percentage of the GPU's resources. So that's a nice capability, but it's not in place yet. The GP100 GPUs, the visualization ones, those are shared among all jobs on a visualization node. We don't we don't schedule those in an exclusive manner. And that's because visualization jobs tend to be kind of on and off. And also, if you're running a remote desktop that happens to use the GPU to help render the desktop, we don't want that eating up an entire node for something that's pretty low resource. So those are shared. For the things that are exclusive means that your job is also restricted to the resources that you request. So if I ask for, say, 10 CPU cores, if I run 20 MPI tasks in my job, those 20 tasks are still limited to the 10 CPU cores. So there's going to be some sharing in there. And if I'm using hyperthreading and that's effective for my workflow, maybe that's okay. That's just something to be aware of, is that you can't break out of this resource containment that you're in. Whereas in a share job on Cheyenne, you can kind of use as many resources as are available at any particular time. There is one caveat to that, though. So in terms of node memory, the fact that we have that NVMe swap space, the solid state disk, that does allow your job to proceed even if you run out of the memory that you've requested, but it's at the cost of pretty significantly reduced performance. So that's something to be aware of. You know, if I'm asking for 10 gigabytes of memory, but my job uses 20 gigabytes, it's probably not going to fail. But once I exceed the 10 gigabytes and I'm starting to use that swap space, my performance is going to go down. So, you know, if you see performance that's slower than you're expecting, I would take a look at memory usage. That's oftentimes the reason for that. Okay. So just to summarize, we do have per user resource limits for each of the job classes. And these are really intended to ensure that we have short job dispatch times in the scheduler. And then also it's there to ensure a fair distribution of Casper's resources. Casper tends to be fairly bursty in its usage. So during the working hours, oftentimes the resources will be quite constrained. But during the off hours, it's quite a bit easier to get a job through. So these should hopefully be a lot more flexible than the restriction that we had in Slurm, which was just a 36 job restriction. So for the HTC category, you can see that this is a category where you're asking for, you know, less than 360 gigabytes of memory, less than 36 NCPUs, and no GPUs. And your concurrent limits there are, you know, a certain percentage of the total resources on Casper. So, you know, these are the numbers for the current size of Casper, but that will grow as Casper grows. For large mem, the key use limit there is that you can have up to 5 jobs eligible to be scheduled. And you can have more queued, but that means that only 5 of your jobs are actually like gaining priority as they wait in the queue. So that's a way to keep people from dominating those 2 nodes, since it is a pretty limited resource. For the Viz, and that should be an S, apologize for that, not a Z. For the Viz, this is the GP100 types, and you can ask for 1 to 2 GPUs from your running jobs. And again, that's just so that we make sure people can get a desktop in a reasonable amount of time, and also a visualization node in a reasonable amount of time. And then for the GPUs, the V100 types, you can ask for up to 16 GPUs in use by running jobs. So that'd be like 4 full 4x jobs or 2 full 8x jobs.
Brian, we have a couple of questions stacked up here.
Sure.
Katie asked, do you have to use the -- exclusive flag with exec Casper, or is that built into the command?
So yeah, in Slurm, the exclusive flag would give you exclusive use of a node. In PBS, if you want exclusive use of a node, you really have to ask for the resources on that node. There isn't like a ask for a limited number and get exclusive use, because by default it's shared. You can use the place statement to affect change in that regard as well. But I'd have to play around with that a little bit to get the exact syntax down for you. So I would say send us a help ticket on that one, and we can work with you to get you the proper formulation for that. But I would say, you know, if your job fits on Cheyenne, that's really the better place for exclusive jobs. And it's only if it, like, you need more memory than Cheyenne can support, or, you know, you need GPUs, then you know, then of course we'll work with you there.
Okay. Good. And then Seth asked, there are times when I'd like a process not to use swap space, but to instead fail and let him know if it runs out of memory. Is there any way to do that?
Yeah, so I think I don't know if there's a native way to do that in the scheduler, but there are certainly ways to limit your processes to a certain amount of memory usage using Unix commands. Again, I would say it's a little out of scope, but send us a ticket and we can work with you on that one. But yeah, I don't think you can do that natively in PBS. Okay, I'm going to go through a couple of things quickly that aren't really PBS scheduling, but I just want to make sure that people know that these things haven't really changed. So if you want to get a virtual desktop, there are multiple options. You can use FastX, which is our web or programmatic interface to get a login type session. This has low resource requirements, or this is if you have low resource requirements in your desktop session. It's really like a login instance, but just a GUI version of that. But you can submit PBS Pro jobs from that desktop session to access more resources. Alternatively, if you want to do something more intense like rendering or other resource-intensive tasks in a remote desktop, you can use our script VNC Manager, which will help you set up a Turbo VNC session, a Turbo VNC remote desktop. And in this case here, I've got a GNOME desktop that I'm running Vapor in and doing some stuff like this. So you can use X forwarding to use a GUI application, but your performance generally is going to be really slow. So we recommend that you get these virtual desktops. And details on how to use these are available in our online documentation. But the important point is that the use for these really hasn't changed very much. In VNC Manager, you would use PBS flags now to specify specific resources rather than Slurm flags, but otherwise they work the same. And also just an update on the Jupyter Hub. So this, will also be for Casper sessions. We'll be switching to PBS for any of your batch submissions by April 7th. So on April 7th, that's when we're going to retire Slurm, and as a result, the Jupyter Hub instance will change. But that in Jupyter Hub, that's a lot of those details are abstracted away, the scheduler details. So it should be very similar. There are some other improvements coming to the Jupyter Hub, which I won't get into here, but in terms of the scheduling piece, it should be a pretty seamless transition. I just wanted people to be aware of that. So now I'll just talk a little bit about getting information from the scheduler. So, deleting jobs is very simple. You can do QDEL from Cheyenne, from Casper, or you can do QDEL Casper from Cheyenne, and then provide a job ID of a Casper job. If you want to show active jobs, you can use the QStat command, and this, on both systems, we have this cached every 10 seconds, so there can be a little bit of a delay in its update, but that's really just to take some load off of the scheduler. Now, the important thing to note here is that you can, with QStat, in a basic way, show jobs running on the opposite server using this @server notation, but this is only supported for certain options. So like the -U for user, wide form output, you can get the status string, a node list, and recent historical jobs with this -X. But if you use this @server, you can go across, and I'll show you what this means in this example. So if I'm on the Casper login and I run QStat-N, that's going to show my running jobs on Casper because I'm not specifying a server. But let's say I'm on the Cheyenne login and I want to show my jobs, so -U user, and recently completed jobs using the -X, but I want to show my jobs on Casper. I can do this @Casper statement here at the end, and that'll show my Casper jobs instead of my Cheyenne jobs. And that actually works in reverse too. I can do an @Cheyenne from Casper and get a list of my Cheyenne jobs using QStat. So that's a nice little way to get a quick summary of what you have running on the opposite system. And that sort of notation is what should be more universal once we have that multi-server capability running. Now, the thing about QStat is it only provides you jobs, even with that -X, it only provides you jobs in the last couple of days. PBS itself doesn't really provide an equivalent to Slurm's saccount command, and that's the command that Slurm has to really query the accounting logs and get past historical records. So we've maintained this QHIST command on Cheyenne and on Casper to query past jobs. So by default, QHIST will output all jobs from the current day, but it has arguments to change the time period and filter jobs by the user, the project, the queue, and more. So I could specify a number of days of past history that I wanted to look over, or I could specify a period with a start and an end date, and then have various filters on that. And the nice thing is QHIST allows you to quickly query your CPU usage and your memory usage of your past jobs. So this is a really quick way to get like an idea of the resources you're using. And just to show some examples of this, if I'm on Casper and I run QHIST, I give my username. Let's say I want to look over the last week, so I look over the 5 days of March 22nd to 26th, and then I sort the jobs by memory, and I just pipe that into head and get the top 6 lines. Now I've got my top 5 memory use jobs on Casper. from last week. So this, you can make some pretty powerful combinations here. And let's say, I'm particularly interested in this top memory use job. I can then run QHIST again. I can specify just the 23rd, which is when this job ran. This is 23rd at the time. And then give it a particular job ID and ask for the long form output, and I can get more details in this long form output. So if you run QHIST-H, it'll give you a summary of all the various options, but it's a pretty useful tool. One thing to note is that QHIST will only show you records from the current server. So if I run QHIST on Casper, it'll show me Casper records, and if I run it on Cheyenne, it'll show me Cheyenne records. It does not have that cross-server capability. And that's because the accounting logs are stored on disk that's only on each particular system. So just to summarize, the basic transition from Slurm to PBS commands, I've lined these up to be basically equivalents. So, your SBatch will become a QSub, your salloc srun will be a QSub-I, or alternatively execdav will be exec Casper. SQ QStat, scancel QDel, and saccount QHIST. One thing I didn't mention in previous slides, but for MPI support, the MPIs do integrate with the scheduler on Casper. So all of our open MPI versions from 4.05 and lower will still have Slurm MPI support, but moving forward, any open MPI version that's greater than or equal to 4.10, and that's already 4.10 is the latest version on Casper. It'll be built with PBS support, and we're also starting to include MBAPICH 2 as well. So that's another MPI option that will have PBS support. And then, again, Jupyter Hub, FastX, VNC Manager, and then the account that you charge to, the project you charge to. This is all migrated from Slurm to PBS, and it's largely invisible to you as a user. So just be aware that we're migrating these things; they're not going away, but the changes should hopefully be pretty minimal. So just to wrap up, I like to kind of give just a heads up on some things that we've already seen when users are migrating. Using QSub on Cheyenne when attempting to submit to Casper, that's going to produce an error. You'll get an unknown queue message at submission time. That's because you'll be submitting to the Casper queue, but the Casper queue doesn't exist on the Cheyenne server. So you need to run that QSub Casper version. Obviously, if you use QSub on Casper with a Cheyenne job, you'll see the same thing, because like the regular and economy and premium queues aren't available on Casper. So if you request an invalid resource amount or combination, let's say I asked for 2 GPUs in my chunk and a GPU type of GP100. The problem there is that we don't have any nodes that have more than one GP100. So this is not a resource request that can be fulfilled. And depending on the specific way that it's problematic, the job may be rejected at submission time, but it may get accepted and end up in a hold state. So basically, it looks like it's submitted, but the job just kind of sits in the queue. We'll probably do some work to clean those up in the future, but for now, I would say if you're running a new job configuration, one that you haven't run before, it's a good idea to verify that it's eligible after you submit. You can run QStat, and if the state is H, that means it's in a hold state, which can happen because you have a dependency on it. But if you don't have any job dependencies and it's in a hold state, then odds are it's not a valid type of job. Another thing is, as I mentioned before, requesting less node memory than the application requires. So in this case, again, the job is unlikely to fail because of that swap space. The swap space is limited as well, so if you use an exceptional amount of memory, then you can still get it to fail. But odds are it won't, but your performance will be significantly decreased because the RAM is exhausted. And that goes to Seth's point that you can restrict your processes to the RAM, but that is kind of outside of the scope of the scheduler. And also, if you're just moving a Cheyenne script to Casper in a very quick way. You know, we've seen some folks, they keep their Cheyenne module loads in the Casper script, like they might load the MPT module for MPI, but MPT is only available on Cheyenne, so that script is going to fail right at the start because the module load can't be completed. So, you know, while it's easier to migrate a Cheyenne script to Casper and vice versa, you still do have to do a bit of legwork there to make sure that you aren't doing something that's system specific. So that's just something to be aware of. And you may want to mark your job scripts appropriately to make sure that you keep that, you know, you might use like an extension like .Cheyenne and .Casper or something like that to keep it straight. Whatever system you think is going to be easiest on you. And like I said, yeah, for that particular instance, the job will fail with an LMOD error, a module error. So that's all I have. You know, certainly I'm sure we'll find more things as we continue this migration. You know, again, next Wednesday, April 7th is when Slurm goes offline, and all of the resources will be scheduled in PBS. So that's the most important date to keep in mind in the near future. If you run into anything that you need help with, you know, certainly go to our user support page. Unfortunately, you can't walk in right now because of COVID, but hopefully, you know, it won't be too much longer. You can go to support.ucredit.edu to submit a help ticket, or you can call that number during working hours to get in contact with the help desk and ask us questions that way. And if you have specific questions from today, or if you have feedback on any of these slides, please do send me an email, and there's my email address. So with that, thank you for your time, and I think we still have a little bit of time for any remaining questions that people may have.
Yeah, we have one question. Recently, I used PIG 20.4 and OpenMPI 4.1 to compile and run my programs for PBS, but the simulation failed with a PMI-X version issue. Is this a temporary issue?
Yeah, I saw that ticket. That's something that I haven't been able to, that's the PGI compiler. That's something that I haven't been able to reproduce with my MPI applications, so I think we need to dig deeper into that with the ticket. But I don't want to say that it's an issue that will hit everybody, but we'll certainly look into that and try to figure out what's going on there with that particular case. You know, PMI-X is included in OpenMPI, so the fact that it would be using a different version is strange to me. But yeah, we'll certainly get that sorted out. And if there is any issue in that installation, then you know, we'll update people accordingly.
Okay, and then Frank asked a question that it'd probably be better if you read it, Brian, rather than me trying to read it out loud to you. Do you have the chat open?
I do. Okay. How would I translate the following Slurm to get 12 OpenMPI threads in PBS? Right. So, okay. So you've got one node, one task, and CPUs per task equals 12. So in this case, yeah, this would all go into that select statement. And let me close this and go back to that slide. Let's see. I'm going to go back. This is probably a good place to go. So we have the select statement, and for that particular request, what I would do is I would select one chunk. I would ask for 12 NCPUs, one MPI task, and 12 OMP threads. And that will give me 12 execution threads, but only one MPI task. So that would be the PBS equivalent of that Slurm specification. Now, if you're used to PBS, you'll know that if you don't set OMP threads explicitly, it will inherit that value from NCPUs. So I could just say NCPUs equals 12 and MPI tasks equals 1, and that would be the same. But you know, it's sometimes for clarity, it's nice to be explicit. Okay. Any more questions, Mick?
Yeah, Gian asked another really good question here. If our login nodes are Cascade Lake CPUs and we want our codes to run on Skylake CPUs, should we compile our codes on a compute node instead of the login node?
Yeah, that's an excellent point, and I would say yes. You know, there are options available to the various compilers. You know, in Intel, you can do the I believe it's the -XAVX 2 Core 2 or something like that. So you can force the optimization level in the compilers. In GCC, it's march, but those details can get a little tricky. So a lot of times it's nice just to let it do its native optimizations and compile on the architecture that you're using. And in that case, you know, I could ask for a couple of CPU cores in an interactive job and use my CPU type equals Skylake here, and that'll get me the access to that. So that is something to be aware of. Hopefully you're not having to do too many compilations in this workflow, but you know, if you were, then that might be a case of using job dependencies, for example.
Okay, one more good question here. Katie asks, I read somewhere that campaign storage will be accessible from Cheyenne at some point. Is that still the case?
Not sure where that was stated, but that's not in the planning right now, no. So campaign storage will be accessible from Casper, and that's not going to change, but there are no plans to make it accessible on Cheyenne. It's also accessible on the data access nodes as well. So, you know, that wouldn't be a place to do computing because those are virtual machines, but that is another place where you can do data movement and things like that. So that's a good point. Yeah, I guess that's another use case where you would specifically target Casper and not Cheyenne in this scheduling setup, is if you have tasks that need to interact with campaign storage. All right, Mick, have we exhausted the questions?
Yeah, for now we have nothing new.
Okay. Well, you know, I'll stay around till 10, but I think we can call it a session. You know, again, I just want to thank everybody for their time. And if you have any follow-on questions, feel free to contact us in any of the means that I show in this last slide here.